Welcome to my distillation procedure video. I'll start with a procedure for a simple distillation, which is how we separate a non-volatile solute from a volatile solvent. Remember, you get one theoretical plate with a simple distillation. So the first thing you'll do is obtain a round bottom flask from your microscale kit. It may look about like that. You'll add the solution to the round bottom flask to be distilled, and it's a good idea to put a boiling chip in there. So put the boiling chip in there to keep the solution from pumping as it boils. And there's your solution. Now we're going to add a distillation head, or condenser, to the top of the round bottom flask, and we connect that using one of our rubber connectors you've probably already used, which is what we attach to the ring stand. And there's a couple of different condensers that you can use in your kit. One of them looks something like this. It's got a curved arm that comes off to one side, like so, and it opens up over here. And it's open on the top as well. And at the end of the condenser, at the open end, you're going to add a receiving flask. And I recommend using something with a narrow opening, so one of your small Erlenmeyer flasks can go here, one of the conical Erlenmeyer flasks. It's a terrible Erlenmeyer flask. Now here's the tricky part when you're setting this up. The most tricky part is that you really should cool the Erlenmeyer flask in ice water. And so on one side you'll be heating this, and on the other you'll be cooling in ice water. And you want the level of the ice water as close as possible to the outlet, or even above it if you can, the outlet of your condenser. The reason for this is that often what's coming out of these small condensers is the vapor, not the actual condensed liquid. And the vapor, of course, can rise and go out into the fume hood, and that's particularly true when you're doing this in the fume hood because you've got lots of air blowing over this. And so we want this receiving flask cool in the ice water so that when the vapor comes out, it immediately condenses and drops as a liquid to the bottom rather than going off into the atmosphere. It's a little bit tricky setting this up. Now you're going to be heating the distillation flask, obviously, and there's a few ways of doing that. Usually what we've been using over the years have been sand baths. And there's a couple of different ways of setting up the sand baths. One is there's sort of half cylindrical heating mantle that we use. Looks kind of like this. And there's sand all around in the center of this. And it's a good idea to get the level of the sand close to the top of the level of the liquid. Now, importantly, there's a plug that comes out of this, a cable with a plug. And what you do not want to do is plug this directly into the wall outlet. This goes into what's known as a variac, which enables you to control the temperature here. If you plug this directly into the wall outlet, then this gets very, very hot, too hot rapidly. You control the temperature of the sand bath using a variac here. So I've seen a lot of students make that mistake over the years. One more thing we need to talk about in the setup of our simple distillation apparatus is placement of the thermometer. So there's another little rubber adapter that goes on top of the hole in it, that goes on top of the condenser, and it's through that you place the thermometer. So that goes through the hole. And the placement of that's really important. You want the bulb of the thermometer to be bathed in the vapor that is condensing up here, and you'll see a reflux as the liquid heats up during the distillation. You'll see a reflux ring rise up here. The bulb of the thermometer has to be bathed in that reflux ring, so it's a good idea to have the bulb beneath the level of the bottom of the side arm coming out of the condenser. So right about there is the tip of the bulb. Anyway, you want to keep an eye on this to make sure that the bulb is immersed in that vapor as it rises up and condenses. So one more thing I should mention is there's another way, since this side arm on this particular condenser is not very long, there's another way you can set up the condenser, and I'll just draw that off to the side. There's another piece of glassware with a shorter side arm to it. Comes off like that, and it's open on top, so you can put the thermometer with its adapter up here. And you can use another rubber adapter here to attach a longer tube. So there's a long, thin tube, not the longest one, it's the second longest one we use. And the advantage this gives you, if you want to do it this way, is it moves the receiving flask over here farther away from the heat source, and sometimes that's a little bit easier to set up. You want to get the tip of this, though, inside here if possible. And of course, again, you've got to make certain that this is in an ice bath so that we're condensing any fumes that find their way into the flask out of the condenser. So those are a couple of different ways that you can set up the condenser for your simple distillation. And of course, the round bottom flask is down here, the thermometer is up here. So that's how to set up the simple distillation. One more thing I should mention, is that we sometimes run out of these heating mantles, and so you can make your own sand bath from a Pyrex Petri dish. So there's your sand, and that's your Petri dish. And you put the Petri dish on top of a hot plate, which enables you to control the temperature. So one stirring control, one temperature control there. So another thing that we're thinking about doing is replacing sand baths, because sand baths by their nature are messy. Sand always gets spilled. We may be replacing these at some point with aluminum cutouts. That'd be a little aluminum block that has an indentation in it that's just big enough that it conforms to the bottom of your round bottom. So if those are available, use those instead of a sand bath. So that's how to set up the simple distillation. And we will now discuss fractional distillation. So remember, with the fractional distillation, we get multiple theoretical plates. So again, we will set up our round bottom flask in our sand bath. And we put our boiling chip in with our solution to be distilled. Really the only difference this time is that here is our connector, our rubber connector again. You're going to attach to the ring stand. We're using a column. It's going to be packed with copper wool. And this is the same piece of glassware you would have used for the second condenser that I showed above for simple distillation. This is the second longest glass tube in your microscale kit. Don't use the longest one. That's for column chromatography. That's a different size, a different width. Inside the distillation column, you're going to be packing this with copper wool. And you want it loosely packed. If it's too tight, if it's too tightly packed, it takes a long time for the vapors to rise up through, and there's a feature of a column like this. It's called hold-up. And hold-up means that the liquid you're distilling coats the surface of the inert material. And the more inert material you have, the more liquid coats the surface, and you never really get that off. So you lose some of the liquid to what's known as column holdup. And the more inert material you have, the more holdup there is, and the more of your liquid, your distillate, is lost. And so the rest of this we set up just as we did for our simple distillation. We got another rubber connector here, and to the top we add our condenser. And really everything else is the same. We're going to use the same rubber adapter to hold our thermometer in place. You'll position the thermometer the same way. You want the bulb of the thermometer immersed in the vapors as they rise up into the condenser. And you're going to set up the receiving flask in ice water. Should be an Erlenmeyer. That looks like a beaker. Remember that it's good to have a narrower opening to your receiving flask so that you don't lose vapors out to the surroundings. And again, we've got ice water around the receiving flask. That's how we set up the apparatus. And we heat the distillation flask the same way we saw above. A few important points to talk about here. First one is that you're going to be doing all your distillations in the fume hood. This thing gives off fumes. You don't want to be breathing those. The one distillation you can do outside of the fume hood is the ethanol and water. So all distillations in the fume hood except, and you can do this one in the fume hood as well, that's optional, ethanol and water, which is not particularly toxic. So one thing I should have mentioned above with a simple distillation, it's true for a fractional distillation as well, is you never distill to dryness. And what that means is you always want to leave just a little bit of liquid left in the flask. What can happen if you distill to dryness is there can be explosive compounds. Peroxides are common in organic solvents, for example, and they're explosive. And as it distills to dryness, this gets very hot, and anything explosive down here, including fumes, if it gets hot enough, mixed with the oxygen in the air in this flask, can ignite or explode. So you always want to leave a little bit of liquid in the distillation flask before you end the distillation. One thing I neglected to mention about the column here is that this really needs to be insulated as you're doing the distillation, and a good way of insulating it is to wrap cotton, kind of a sheath of cotton, around this and hold it in place with aluminum foil. So there's your cotton insulation. Hold this in place with aluminum foil. And the reason for that is when you're doing this in the fume hood in particular, the air rushing over this cools it down, and as the vapor rises up here, it cools down, it condenses, then more hot vapor comes up, and it re-vaporizes and condenses and so on. It's microscale, so the heat transfer here is fairly efficient. This is a small tube. And so if the heat's being transferred to the air that's rushing by, it never really gets hot enough in here for the vapor to rise all the way into the condenser. So it's pretty important to insulate your condenser doing your distillation, particularly in the fume hood. So a couple more points to mention, and then we'll talk about the process of the distillation itself. Talked about hold-up. Bear in mind that there's going to be some hold-up, and one of the bigger problems I've seen with the fractional distillation over the years, is that there's so much copper in here that you never see the second fraction coming over. So use a significant amount of liquid, and don't pack this too tightly. If you're not sure how much copper to use, come up and show it to me, and I'll tell you if you've added too much or too little. This needs to be loosely packed, but there does need to be a fair amount of copper in there so you get multiple theoretical plates to efficiently separate the compounds, the liquids. As far as the rate of distillation, that is, how fast should the liquid be coming out, condensing into your receiving flask, 2 to 4 drops per minute at this scale, at the microscale. That's our distillation rate. The faster you go, the less likely you are to get an equilibrium of condensation and vaporization in the column here. That is, you reduce the number of theoretical plates, and you end up getting the mixture higher and higher up the column, and it can get up into the condenser, and therefore you don't get good separation at faster rates. So slower is better. 2 to 4 drops per minute is a good trade-off between good separation and time. If you do it any more slowly than that, then it takes too much time. So now what are you going to observe during the distillation? During the distillation, you're going to be recording the temperature and the drops that come over. And so I'm going to plot that over here and give you a couple of hypothetical situations as to what you might see. So a graph of temperature in degrees Celsius versus drops. And we'll pretend that we're distilling, say, cyclohexane and toluene, which is one of the ones you may be doing in your lab. So as soon as you start to see drops coming over here, it takes a while, but you'll eventually see the liquid come up into the reflux ring, come up into the condenser. Make sure that that bulb is bathed in the reflux ring. It's below the level of the bottom of the side arm out of the condenser. And as the liquid condenses and revaporizes off the tip of the thermometer will rise to the temperature of that liquid. And so if it's pure cyclohexane, the temperature you would be seeing for the drops coming over would be about 82 degrees, which is the boiling point of cyclohexane. Now, Occasionally you might see the first drop or two coming over at a lower temperature, and there's a couple of things that can cause that. One is that it's pure cyclohexane, and that the thermometer is just taking a while to rise up to the temperature of the vapor. So that's a possibility. The other possibility is there might have been another impurity, usually water, in the solvent mixture, in the mixture of the two liquids, and that might be forming a low boiling point azeotrope that's coming off a little bit before the pure liquid. And so the first drop or two might be contaminated with moisture, for example. And for that reason, often when people are doing distillations preparatively, they will discard the first few drops that come off. Now we're doing this in microscale, so the first few drops might be one drop. So if you get something off coming out at a very low much lower than your lower boiling point fraction, you might want to do that. So as the distillation progresses, you get drops ideally at the temperature of the lower boiling fraction, and then one of two things may happen. Once the last of the lower boiling fraction comes over, the temperature may just collapse, might drop very rapidly. And at that point, you should see nothing more coming over, because what's happened at that point is the lower boiling point fraction, in this case the cyclohexane, has all been forced over. There's a little bit maybe perhaps left on the column. And there's nothing left up here, so there's no hot vapor anymore, so the temperature falls. At that point, you can raise the temperature of the heating mantle, and that will force the higher boiling point fraction up the column and into the condenser. And once that happens, the temperature will rapidly rise, and you'll get a series of drops coming off, ideally at one temperature. And if this was toluene, that'd be coming off at about 111, 112 degrees, I'll say 111, which is about the boiling point of toluene. And that goes until you've got just a little bit of liquid left in the flask, and then you stop. Oh, and I forgot to mention, very importantly, once the temperature falls here, that's when you switch flasks. Okay, so at this point right here, okay, when the lower boiling point fraction is gone, you switch or change flasks, receiving flasks. You have to do that, of course, because you want to separate the two liquids. So that's kind of an ideal situation. What often happens, though, is not this. What you might see, and what you're likely to see when you're doing the distillation, is instead of the temperature collapsing, it will slowly start to rise. So you might see a drop coming off a little bit higher, a little bit higher, a little bit higher, and a little bit higher, and so on, until you reach the boiling point of the higher boiling point fraction, in which at that point it levels off, like so. So what's happening here? In this region right here, where the temperature is ramping up, what's coming off in this region is a mixture of both compounds. So you started with pure lower boiling point fraction coming off, cyclohexane in this case, and that should have gone into the first receiving flask. Immediately when the temperature changes, begins to go up, you switch flasks. So again, we're going to switch flasks at this point, because we don't want the mixture contaminating the lower boiling point fraction. Remember, the whole point is to get pure liquids off. And so I would use the same flask throughout the range where you have a mixture of compounds coming off. And then, once you get the boiling point of the higher boiling point fraction, again, you switch flasks. And everything that comes off after that point is the higher boiling point fraction. And so in flasks 1 and 3, you have pure liquids. In flask 2, you have a mixture of the compounds. So, one last point here. There is a technique that you can use for distilling high boiling point liquids that reduces the boiling points of those liquids. And this even works with solids that have significant vapor pressures. And that is known as vacuum distillation. In other words, you can hook an apparatus like this up, set it up so that it's airtight. You hook it up to a vacuum pump. It's reducing the pressure above the liquid, or even the solid, reduces the boiling point of the liquids. Because remember, boiling point is that temperature where the vapor pressure of the liquid equals the pressure above the liquid. That reduces the boiling points, and you can do the distillation at lower temperatures. So we're not going to be doing that, of course, but that's another technique if you ever need to distill higher boiling point liquids, or even solids. The solid will melt at the reduced temperature and lower pressure. and then we'll distill. So if you've got volatile solids, you can sometimes separate those also by fractional distillation. So hopefully that makes sense. If you have any questions, come by and see me, and otherwise make sure this is in your lab notebook, and I will see you in the laboratory.